Thank you so much. It's really an honor to be in such an amazing event. And today I want to start with a question. That is, how can we understand the shape of something if we are standing on it? This may seem like a very abstract question, but we can rely on our everyday experience to really explore it. I mean, if we look around, I have to say, especially here in Estonia, everything looks very flat. Like, if we go from Tartu to Tallinn, you don't feel any kind of curvature in the road. It's like you're with the car, everything, it's like completely flat. So if someone comes to you and asks you, how do you know that the earth is round? So before you become a flat earther, like I'm gonna give you a very quick example. And we can imagine two friends, Anna and Jan. One of them thinks that the earth is flat, and the other person thinks that the earth is round. So they decide to make a bet and say, okay, let's go to the equator, let's start in different points, and let's start walking parallel to each other. So the person that thinks that the earth is flat has studied high school geometry, so they know that two parallel lines, they will never meet. So one of them says goodbye forever, we will never meet again. But they walk towards north. They go through mountains, deserts, the sea, ice. And then they meet again in the North Pole. And they're very happy, but of course, the flat earther is like, no, you cheated, you deviated, that's why we met again. But no, they check, and they see that they have walked straight all the time. So they realize that it's a consequence that the earth is round. And this is amazing. It's like they, standing in the object itself, they have managed to understand that it has a shape, that it's not flat. But this is because they have gone to a scale that is comparable to the whole system. But when you are like in a very local scale, you are not able to see this. And this is at the core of differential geometry. Differential geometry is a field in mathematics that studies the shapes that go beyond the flat space and allow you to understand very complex shape. And really the deep core of this is that locally you can build a flat plane, but that it's not going to fit the whole plane. And it's how these planes, they are related, that it tells you the whole shape of space. And the beautiful thing about differential geometry is that it's an idea that can travel between fields. I'm Pepe Maldonado, research fellow in computational neuroscience in this very same house, in the Institute of Computer Science. And today I want to take you through this travel along fields on how geometry can really be applied to different fields of knowledge. And it has also been my personal journey. I studied as a researcher in theoretical physics, specifically in gravity. And for many years, when I thought about differential geometry, I thought about gravity. But because really, differential geometry is at the heart of what we understand of gravity theory, especially the theory of general relativity. And we can understand it by a thought experiment, that we can imagine ourselves in an elevator. Everything is going well, chill day. You know that if I take my phone, I can drop it and the phone will go down. Gravity is working. I'm not going to do it because I don't want to pay for another phone. But we can imagine that then the cable breaks. It's a very dramatic situation, but at that moment you don't realize, because at that moment what you feel, it's like completely weightless. And you're like, wow, this is amazing. And at that moment you can throw your phone and the phone will float with you, no? So you're like, okay, what's going on? Gravity has disappeared. Indeed, kind of has, because this is the thing about gravity, that locally it can be removed. But globally, we see their effects. Let's say, for example, if I was here and what I was attracted by, instead of the Earth, it was the camera that is at the end of the room, then I could see also other objects being attracted by the camera, and I could see this effect. Why? Because then, like, I'm in the same scale as the whole system. In the case that I'm being attracted by Earth when I'm in the elevator, like my scale is much smaller than the whole system. And this probably rings a bell, and you go again to Anna and Jan, where if they are in a small scale, going from Tartu to Tallinn, they cannot see that the Earth is round. But when they are in the whole system, they can see it. So that's why we can pose gravity as being a consequence of the space having curvature, and that we move along the lines of minimum length. But this is the beautiful thing, that we don't see this curvature. You know, we just leave it and we see the effect on it. But I promised you that we were going to switch fields, as I did myself. And you may wonder, when I told you about what I'm doing here, what is a physicist doing in an institute of computer science studying biology? I wonder that myself sometimes, but but I can tell you that since I started this journey, I realized that we use the same mathematical tools, because if you think about it, like, the brain has to understand space also. And it has to understand it from its own perspective. Let's say we cannot see the world from above and see, yeah, the world is like this, I can move like this, I can go like this through the door. No, what you have access is the things you see, like the cues that you have. I know that if I want to go through the door, I cannot go following a straight line. I will have to go straight and then left, because there are things in the middle, there are obstacles. So curiously and beautifully, like, for me, it was very shocking to see that the brain is encoding space in different kind of signals. One of them, it's the place cells. It's very self-explanatory. They didn't think too much the name. It's like, if you are in a certain place in space, you get an activation. But if I get an activation of this cell here, when I'm here, it doesn't get activated. But then they found another kind of cells that they're striking. They produce a grid pattern in a room that a rat is exploring. But this is crazy. Like, it's like the brain hasn't entered this space, and then it's able to produce kind of a map/pattern that follows this room. Like, this is crazy. How is this possible? But we can think about it in a term of some kind of coordinates of space. Let's say that we have access to the place cells, no? And here I get a certain activation, and I start moving far away from there. I get less activation, but at the same time, the next place cell, the one of here, it's starting to activate. So I get some correlation between activations. But also I know that here I'm surrounded by many place cells, but if I go very near here, that I cannot move that way, I'm only surrounded by less place cells, because the ones here like cannot get activated. So by the correlation between cells, between place cells, you really are understanding already the structure of space. And the thing is that when you want to understand correlation in space, there is a mathematical object that it's very useful, that it's called the Laplacian. The Laplacian, you can think about it as an operator that cares about how a point is connected with its surrounding. For example, it appears in the heat equation. how heat it's distributed into a room. Of course, the heat distributes differently if there are corners, if the room is shaped differently, if there are obstacles. So you really need to know which kind of space you are. And the cool thing about this operator, as all the operators in mathematics, is that you can wonder about the functions that are not affected by it, let's say, because these functions already encode what this operator is encoding. So if you have the functions that are invariant under this operator, they are gonna already encode the shape of the room. So there are studies that have related these functions that are invariant to the Laplacian operator to the grid cell activation. And the cool thing about these functions is that they give you an internal set of coordinates. And coordinates that really what they care about is about the real distance on how you would move in space. Because if we take the usual distance in this space, like the blue and the red dot, they would be very close and very far away to the green one. But in reality, if we want to go from the blue to the red one, we cannot go. We have to go around this and then reach the red one. So these coordinates, if you calculate the distance in these coordinates, they are gonna tell you that indeed it's easier to go from blue to green than to blue to red. But of course, we are in the Institute of Computer Science, so I have to talk a little bit about computer science and how these coordinates can be useful in computer science algorithms. Because, for example, when we are studying, like we want to identify an object, but we don't care about the pose that it has. No, you want to identify me here. You want an algorithm that identifies that it's me, but you don't care if I'm like this, I'm doing this. You know, like you want the algorithm to keep working, no? So it's like what you can do at that moment, of course, is to use internal coordinates that they just care about the correlation between the different points of the body. Let's say my hand and my shoulder, like here, let's say in a space, they may seem close, but the correlation between themselves is the same now as it's now. So this helps you like create this kind of analogs between shapes, even if they have like different pose. So what I hope you have learned today is that even if geometry it's like a very abstract field, like it's this abstraction that it really lets it travel along different fields. And this has been like my own personal journey and has taught me like things beyond research and beyond academia. Like of course, when I switched fields from gravity to neuroscience, like I was very scared. It was new ways of studying things, new literature. But I started understanding that I could say something based on my own previous knowledge. So I hope you are not afraid to express your opinion in any context that you are, because your opinion it's going to be valuable independently of the place that you come from. And really, like ending in a more philosophical note, we can think about our own experience as being our local world, that of course is gonna be flat. And it's only by interaction with other people that we are gonna understand the true shape of the world. So I hope we keep creating spaces like this of cooperation and dialogue, and less spaces of confrontation. Thank you so much.